So in this simple illustration here, we can see what's going on in terms of current and voltage, actually just the voltage across each of the individual components, capacitor, inductor, and the total of the two. So as we said before, you can see the capacitive, the voltage drop across the capacitor, voltage drop across the inductor, which is larger, and the voltage drop across the combination of the two, which bears out that the drop is going to be less and match what we talked about, the reactance. Looking at the sinusoidal waveform for each, the blue being the inductor voltage drop, the green being the total of the two, and the red being the capacitive, we can see first off the phase relationship between the two, the inductor and the capacitor, and we can see that because the green is more positive here, the combination of the two, we can see that the difference between them actually brings down the inductive component closer to the capacitive component. So in this example, we take a look at, again, another simple series circuit. In this case, we have all of the reactances and the real parts in ohms. So all we have to do now at this point is start combining the terms into their phasor form, the rectangular phasor form. So the sum of all of the resistor and capacitors and inductor reactances, 75 ohms, J 25 ohms, minus J 60 ohms, gives us our total then of 75 minus J 35. So again, our next step is converting the rectangular form into the polar form. We can see then, as we have done before, we find the total inductance, the total reactance between the inductor and the capacitor. In this case, the difference in 25 and 60 ohms gives us a absolute value of 35 ohms. When we take those values, run them through the Pythagorean theorem and the inverse tangent, we end up with a total resistance, impedance, 82.8 ohms at an angle of minus 25 degrees in our polar form. Now we can go through and use the Ohm's law relationship. They want us to find the current and the voltage across each element, express each quantity in polar form, and draw a complete voltage phasor diagram. So now, using the Ohm's law relationships, we can solve for current, the source divided by the total impedance, which gives us 121 milliamps at an angle of 25 degrees for the current, and then each of the individual voltage drops. The voltage drop across the resistor, I times R, then we can combine our terms here. 121 milliamps, 75 ohms gives us 9.08 volts, and the difference in the angle here, or the sum in this case, gives us 25 degrees. We do the same thing for the voltage drop across the inductor and the voltage drop across the capacitor. Again, we've got milliamps and ohms, milliamps and ohms. When we combine them, we get 3.03 at an angle of 115 degrees and 7.26 volts at an angle of minus 65 degrees. So now it's just a matter of laying these out on a grid or drawing the phasor diagram. Typically we try to keep these in some kind of scale, but sometimes that's pretty difficult to do. You can see we've laid it out. We've got our source along the x-axis. We've got the voltage drop across the resistor here, forming an angle of 25 degrees at 9.08 volts. And then we've got our inductor and our capacitor voltage drops opposing each other in opposite directions at an angle of 115 and then 65 in the negative direction. So now, what we're going to start seeing here more and more is this phenomenon, if you want to call it that, of resonance, where X sub C and X sub L start to cancel each other, resulting in a purely resistive circuit. So at some point, when X sub C and X sub L approach each other's value and they become equal to the rest of the circuit, it looks like they're gone. They're moving energy back and forth and not doing anything in the circuit, and have been nullified. So if we look at this example for this series RLC, we want to determine X sub C and the total impedance at the resonance. So we know X sub L and X sub C will have to be the same value at resonance. Well, since we're given X sub L as 500 ohms, we don't know what X sub C is, other than the fact that we're looking for what's going on at resonance, the total impedance. X sub C then equals X sub L and is 500 ohms. So the rectangular form, Z then at resonance, notice the little r down here, Z at resonance is the vector sum of the resistor, the inductor, and the capacitor. 100 ohms plus J, 500 ohms, gives us then a total of 100 at an angle of 0 degrees. Of course, the step that's missing here is doing the rectangular to polar conversion. You go ahead and do that conversion to prove that that is in fact the value. The impedance at resonance then is equal to the resistance. The reactances are equal in magnitude and therefore cancel out. So if we look at just the simple representation here, X sub L and X sub C in cancellation at resonance, we can see then with each alternation of the sinusoid of what's going on here. In this case, the total becomes 0 volts dropped, 0 volts dropped in each case. And we end up in a perfect relationship at 90 and minus 90. The two cancel out, the magnitudes cancel out, and all we're left with is the voltage across the resistor. So at the resonant frequency F sub R, the voltages across the capacitor and the inductor are equal in magnitude. Since they're 180 degrees out of phase with each other, they cancel each other, leaving 0 volts across the L and C combination, point A to point B in the circuit. The section of the circuit from A to B effectively looks like a short at resonance. So at resonance frequency, X sub L equals X sub C. If we take our two relationships and set them equal to each other for inductive reactance on the left, capacitive reactance on the right, and we start combining and simplifying, we end up with 2 pi FL. Move our terms around so that we have the frequency and the 2 pi in the denominator. So in this case, we're going to multiply through by F sub R 2 pi L, F sub R 2 pi L, and we get a value of the frequency at resonance squared is equal to 1 over 4 pi squared L times C. Take the square root of both sides, we end up with the resonant frequency is equal to 1 over 2 pi LC, the square root. So with this, again, write this down in your notebook, keep track, especially of that last step here, because that is going to be your key expression for solving for resonant frequency, inductance, and capacitance in future problems. We can see here, find the resonant frequency then for the circuit. We're given 100 ohms, 47 picofarads, 5 millihenries. Okay, so at this point we need those two pure values for the units. We plug them into the relationship, 5 millihenries, 47 picofarads. Run it through your calculator, you get 328 kHz as the resonant frequency for this circuit. So with series RLC impedance, you can see we add our total impedance then into the diagram that we saw before. At this point, you can see that the total impedance equals exactly the resistance in the circuit, which occurs right there at the resonant frequency. So when we come back, we'll move forward with more examples of series resonance.